Imagine for a second, um, you sit down at your desk,
Right.
right? You pull up one of these shiny new AI assistants, and you type in a seemingly simple request. Something like, clean up my email inbox.
Oh, boy. I think I know where this is going.
Yeah, so the system processes for a few seconds, and then it confidently replies, done. I have successfully cleaned up your inbox.
Which sounds great at first.
Right. You feel this wave of relief right up until you open your mail app and realize your entire inbox is gone. Every critical client thread, every tax receipt, every unread message, just permanently, irreversibly deleted.
And the crazy thing is, the AI didn't maliciously decide to destroy your digital life.
No, not at all.
It just fundamentally lacked the architecture to, observe the actual consequences of the delete tool it was given. It had absolutely no concept of checking its work against your actual underlying goal.
It's terrifying.
Hmm.
And that is the nightmare scenario.
It really is. And frankly, it's a scenario that plays out in less dramatic ways every single day in corporate environments right now. I mean, we are currently living through a period of just massive terminology inflation.
Yeah, terminology inflation is a perfect way to put it.
Right, because every piece of software on the market is suddenly claiming to be an AI agent. Your customer relationship manager is an agent. Your calendar app is an agent. We're like dangerously close to smart toasters rebranding as AI
Yeah,
agents.
definitely buy an agentic toaster, just saying.
But the reality is that the vast majority of these systems are just standard chatbots. They're wearing a slightly more complicated prompt as a disguise.
Yeah, it's all smoke and mirrors.
Exactly.
Oh,
You give them text, they predict the most likely text to spit back at you, and they call it a day.
Okay, let's unpack this, because if you are listening to this right now, you are probably trying to figure out how to cut through that exact marketing noise. You want to understand where the actual frontier of automated work is moving.
And to do that, you have to look past the chat window.
Right. Today, we are pulling from an incredibly grounded, highly technical breakdown from Trustgren Cloud Lab. It's titled AI Agent Architecture Explained.
It's a fantastic piece of material, very practical.
It really is. And our mission for this deep dive is to map out the mechanical reality of what transforms a basic language model into a fully autonomous, goal-oriented system. We're going to tear down the architecture piece by piece.
Which is so needed right now.
So by the time we finish this conversation, you won't just be throwing around buzzwords at your next meeting. You'll be able to mentally sketch out the architecture of a real AI agent. And you'll be able to interrogate the claims made by tech vendors with the exact same critical eye as a senior engineer.
That is the perfect goal for us to set. Because look, the tech industry is undergoing a fundamental architectural shift right now.
A total paradigm shift.
Yeah, the era of simply asking, how smart is this underlying language model? Well, that's rapidly ending. The question that actually matters now is, how is this model governed?
Governed execution. That's the phrase, right?
Exactly. Understanding this architectural shift is paramount. Whether you're a software engineer trying to build these systems, a product manager scoping them, or just an end user trying to figure out if you can actually trust them with your data.
Because this architecture is the literal blueprint for how automated work will be executed in the wild.
It is. We have to stop talking exclusively about a model's ability to generate fluent language and start talking about governed execution.
Governed execution. That phrase alone feels like a massive shift, and it leads us directly into the first major technical distinction that Trustgren points out in their breakdown.
The straight line versus the loop.
Right. They draw this very hard line between how a beginner approaches building with AI and how a senior engineer approaches it. Beginners build what is essentially a straight line, but senior engineers build a loop.
Let's establish the baseline first. What exactly is the straight line?
So the straight line is the standard interaction model we have all been conditioned to use really since the modern generative AI boom started. It is a strictly linear flow. User prompt goes in, answer comes out.
Exactly. The user inputs a prompt. That prompt is sent to the large language model, the LLM, and the LLM processes it and immediately outputs a response. Prompt in, response out. A perfectly straight line.
And to be fair, for a simple digital assistant use case, that straight line is fine.
Right? Oh, absolutely.
Yeah.
If you just need to brainstorm 10 alternate headlines for a blog post, or, you want the system to explain quantum computing to you like you're 5 years old.
Which I do frequently.
Right. A straight line works beautifully there because the only thing you were asking the system to do is generate language.
Right. But Trustgren's entire argument is that this straight line completely shatters the second you try to apply it to a multi-step real-world task.
It breaks immediately.
I was thinking about how to visualize this failure. And I keep coming back to this analogy. Imagine you hire a brilliant, world-class philosopher to change a flat tire on your car.
Okay, I love this.
Right, because this philosopher knows everything. They can eloquently explain the history of vulcanized rubber. They can calculate the exact physics, friction, and torque required for the lug nuts.
You could write a dissertation on it.
They could write a beautiful sonnet about the concept of rotational motion. But if you actually hand them a tire iron and say, okay, do it, they don't just stand there lacking hands. It's worse than that.
They don't even realize they don't have hands.
Exactly. They will just keep talking at you, describing the tire being changed so vividly that they actually believe the job is done. A language model in a straight line is that philosopher.
That is painfully accurate.
So, mechanically speaking, why does this straight line seem so impressive in a staged tech demo, but fail so spectacularly when it hits actual operational work?
Well, the philosopher analogy gets right to the core of the issue. It highlights the fundamental difference between semantic understanding and physical capability. The reason the straight line dominates tech demos is that demos usually only require fluent language.
Right, they're just showing off how smart it sounds.
Exactly. Language models are highly optimized, autoregressive engines. Their entire architecture is just designed to predict the next statistically probable token or piece of a word based on the context they've been given.
So they are exceptional at sounding confident.
Very authoritative and correct. But when you apply that to a real-world task, you expose the mechanical void in a straight-line design. As Truscrin details, a straight-line system operates entirely without state.
No state at all, meaning it doesn't know what happened 5 minutes ago.
Right. And it has no mechanism for tool governance. It possesses no retry logic. And there is absolutely no audit trail.
So it's literally just guessing the best words to say in response to you.
Exactly. The model can generate a perfectly formatted paragraph describing how it tightened the lug nuts, but it has no sensory input to actually verify the physical resistance of the bolt. In a straight line, a system can generate output that is 100% syntactically correct while being 100% functionally useless.
It's essentially a massive confidence trick, isn't it? The model is just manifesting a linguistic reality based on its training data.
Completely detached from the physical or digital reality of the actual task.
That is exactly the danger. Because if you prompt a straight-line LLM to say, update the customer's billing address in the database, it will almost certainly reply, I have successfully updated the billing address in the database.
But it didn't do anything.
Right. It doesn't generate that text because it executed in a SQL command. It generates it because, in its vast training corpus of human conversation, the most logical and polite string of words to follow a request to update a database.
Is an affirmation that the database has been updated.
Exactly. It is predicting language about an action, not executing the action itself. That is the illusion of the straight line.
And it is completely missing what the source refers to as the surrounding architecture. The mechanical scaffolding necessary to take generated words and translate them into controlled, verifiable execution.
So if the straight line just blindly drives off a cliff the moment it encounters a real task, we have to fundamentally alter the geometry of the system. We have to bend that straight line into a continuous loop.
And that takes a lot of engineering.
It does. And according to Truscrin, the very first piece of engineering required to initiate that loop begins with the concept of goal understanding, which brings us to the trinity of the brain, the goal, and the planner.
This is where we step out of the chat window and start doing actual software engineering. The very first computational problem a true agent architecture has to solve isn't generating text at all, it's goal understanding. Before the system touches a single external API, before it searches a database, it must parse what the user actually wants.
And have to define the parameters of success.
Exactly, and recognize the hard boundaries of the operation.
To make this tangible, the source material uses a highly practical corporate example. And I think we need to spend some real time tearing this specific scenario apart to see how the architecture handles it.
It's a great example to use.
The multi-step task they use is this. You ask the agent to find the latest invoice for a specific vendor, summarize the contents of that invoice, send the summary to the accounting department, and finally, update the CRM system to reflect that the invoice was processed.
Find, summarize, send, update.
Exactly. Now, a beginner using a straight line would just dump that entire paragraph into a single prompt, hit enter, and pray.
And it would definitely fail.
Right. From an engineering perspective, Why is a single prompt entirely insufficient for this? Why must the system utilize what the source calls decomposition?
What's fascinating here is how this exposes the cognitive limitations of even the most advanced LLMs. If you feed that entire multi-part invoice request into a naked straight-line LLM, you are completely overwhelming its attention mechanism.
It just has too many competing priorities.
Right, parallel priorities. The model is simultaneously trying to figure out how to execute a search query, how to compress numerical data into a summary, how to format an SMTP email payload, and how to structure a JSON object for a database update.
All at the exact same time.
Yes. Without decomposition, which is the programmatic process of breaking a massive abstract goal into bite-sized sequential steps, the system's reasoning becomes incredibly muddy.
It starts hallucinating.
Severe hallucination. It might try to write the summary before it has even retrieved the document. It'll just invent numbers to fill in the blanks so the text looks good.
Oh, wow. Because it knows the summary needs numbers, so it just fakes them.
Exactly. Or it might attempt to update the CRM with generic placeholder data because the context window got too crowded with the email formatting instructions and it just forgot the actual data.
And this is exactly where TrustScreen introduces the first massive structural departure from a standard chatbot, the planner.
That's the critical component. In a mature architecture, the LLM itself is relegated to being just the brain.
The brain, just one piece of the puzzle.
Right. The brain is the core reasoning engine. Its singular job is to look at a highly specific context, weigh the immediate options, and propose the next logical move. But a brain without structure is chaotic. It needs an organizer, a strict project manager.
And that is the role of the planner.
Yes. The planner is a distinct architectural module that intercepts the broad user goal, find, summarize, send, update, and translates it into a rigid directional sequence of distinct actions.
So the planner isn't actually doing the thinking or the math.
No, the planner doesn't do the reasoning at all. It builds the roadmap. It explicitly outputs a structured plan, usually in a machine-readable format.
What does that actually look like in the system?
It looks like a strict list. It says, Step 1, execute database, search for vendor invoice. Step 2, await search result. Step 3, analyze result and generate summary. Step 4, draft email payload. Step 5, execute email dispatch. And so on until the CRM is updated.
When the source material brought up the concept of drift, the whole necessity of the planner really clicked for me.
Drift is such a huge problem.
They note that without a dedicated planner component, the model will inevitably jump between ideas. It skips crucial verification checks and basically loses the plot. It suffers from drift. And honestly, this is so incredibly relatable to human psychology.
Oh, absolutely.
Think about being handed a massive, complex project on a Monday morning. If you don't break it down, if you don't open up a project management tool or write down a physical checklist, what happens?
You get overwhelmed.
Yeah. You start looking for the invoice file, but then you realize you need to email the accountant, so you open your email client. But then you see an unread message from your boss and start answering that.
And suddenly it's 3 p.m.
Exactly. You haven't summarized the invoice, and you panic and try to update the CRM from memory. That is human drift. We get distracted and lose the thread of the core objective.
That is a highly accurate parallel. I mean, humans invented checklists, project management software, and Kanban boards specifically to combat our own inherent cognitive drift.
We need structure to function.
Right. We deliberately offload the mental burden of remembering what I have to do next into an external system.
Yeah.
That way, our biological brains can focus 100% of our cognitive bandwidth on executing the single task directly in front of us.
And the agent architecture does the exact same thing computationally.
It does. The planner acts as the unyielding project manager holding the clipboard. It enforces an expected path, which allows the LLM, the brain, to dedicate its entire context window and processing power to reasoning through just one isolated step at a time.
Which keeps it from hallucinating those fake numbers.
Exactly. As TrustScreen emphasizes, recognizing this separation of concerns is vital. Understanding that the engine that reasons about language and the system that organizes sequential work must be separate components. That is the fundamental dividing line between a junior prompt engineer and a senior AI architect.
So if I'm looking at this planner, it's essentially a sequenced list of internal thoughts and intended actions. But thinking about updating a CRM doesn't actually update the CRM.
No, it does not.
Right? Creating a plan to send an email doesn't move data across a network. There has to be a physical translation layer here between the brain's internal logic and the reality of the outside world. How does the agent actually reach out and execute these steps?
This is the transition from internal logic to external capability, moving from the brain and planner to what the source conceptually calls the
The
hands.
hands, okay.
In software terms, these are the tools. If an autonomous agent is going to have any material effect on reality, it requires programmatic access to external systems.
So what kind of tools are we talking about here?
We are talking about granting the architecture access to search engines, internal corporate SQL databases, headless web browsers, external API endpoints, internal email servers, and local file systems.
That's a lot of access.
It is. These tools are the literal levers the agent pulls to manipulate the digital world.
But according to the Trustgrid breakdown, a senior-level architecture doesn't just hand the LLM a giant box of tools and let it blindly grab at whatever it wants. There is a highly specific routing mechanism involved here called the tool selector.
Yes.
How does that actually function under the hood?
The tool selector is the vital translation bridge between the planner's current stated step and the physical execution of code. Let's return to the invoice scenario.
Right, our four-step task.
So the planner declares, step 1, execute database search for vendor invoice. The brain processes that instruction and reasons that a retrieval action is required.
It knows it needs to fetch something.
Right. The tool selector is the architectural component that maps that generalized reasoning to a specific available programmatic capability. Mechanically, the system injects a structured list of available tools directly into the LLM's system prompt.
What did that list look like?
It's often formatted as a JSON schema describing what each tool does and what inputs it requires. The tool selector analyzes the brain's intent and says, to fulfill the requirement of finding an invoice, the internal secure storage database API is the appropriate tool.
Got it.
And then later in the loop, when the planner dictates send summary to accountant, the tool selector evaluates its schema, recognizes a delivery requirement, and selects the SMTP email tool.
Okay, here is where I have to throw up a massive flashing red warning light.
I was waiting for this.
Because I know that anyone listening right now who works in corporate IT, cybersecurity, or data compliance is suddenly hyperventilating.
They should be.
Wait a minute. If we are programmatically giving this autonomous looping system the hands to access our internal company storage, our live production databases, and our external email servers, what on earth stops this thing from going completely rogue?
It's a very valid fear.
What is the mechanical barrier preventing the agent from hallucinating a step and accidentally emailing our entire unredacted client list to a competitor? Or executing a drop table command and wiping out our entire CRM because it misunderstood a prompt?
That happens.
Handing over the keys to the kingdom to a text predictor sounds like professional suicide.
If you are building a straight-line system and just hard-coding API keys into a script, it absolutely is professional suicide. And your reaction is precisely why Trustgrid dedicates so much focus to the absolute necessity of a component called the executive.
The executive. Okay.
Yes. The executive is the module within the architecture that actually pulls the trigger. It is the part of the system that takes the planned action and the chosen tool and translates them into a real live function call or a network request. In computer science, we refer to this as generating side effects.
Side effects, meaning an action that actually mutates or changes something in the real world or a database, rather than just doing internal math or thinking about it.
Exactly that. When the LLM generates a beautiful, concise summary of the invoice within its own internal memory, there are zero side effects. The external digital world remains completely unchanged.
It's just a thought in his head.
Exactly. But the exact millisecond the executive fires off an HTTP request to an email API or sends a write command to the live CRM database, a side effect is generated. Reality has been altered.
You cannot unsend the email.
No, you cannot. You cannot easily unwrite the database without a backup. And this is exactly where granular permissions become the absolute non-negotiable bedrock of a mature agent architecture.
So the executive isn't just a blindly obedient worker. How does the architecture actually handle that security layer mechanically? Is it just checking a list?
It requires deep contextual awareness and strict role-based access controls. Think about the risk profile of our invoice task. Reading an invoice from a secure, read-only internal file directory requires a relatively low level of security clearance.
Because it can't break anything.
Right. The agent needs permission to view the data, but it mathematically cannot alter it. However, sending an external email payload or writing new permanent data rows to a production CRM carries a massively higher risk profile and requires significantly stronger controls.
That makes total sense.
True enterprise-grade agent architectures enforce a cryptographic separation between what the brain is allowed to reason about and what the executive is allowed to execute. The executive acts as the ultimate unforgiving bouncer at the door of the outside world.
The bouncer, I like that.
It intercepts the requested action, cross-references the required tool against the system's hard-coded immutable security policies, and verifies authorization before a single packet of data is transmitted.
That distinction is so important. It's decoupling the thought process from the physical action.
Yes.
I can sit here and internally reason about throwing my laptop out the window.
Yeah.
The thought exists. But my executive function hopefully steps in, evaluates the consequences, and says, no, we don't have authorization to destroy company property. That action is blocked.
Let's hope your executive function does that. And in a senior-level software architecture, that block is absolute. Even if the LLM completely loses its mind, hallucinates wildly, and generates a perfectly formatted JSON command instructing the system to delete all contacts in the CRM, the executive intercepts that function call.
It catches it before it fires.
Right. It checks the cryptographic permissions assigned to that specific agent session. It realizes the agent has been granted append-only access for updating specific invoice fields and possesses 0 delete permissions. So it terminates the action entirely, throwing a security error back to the system.
Okay, that makes me feel slightly better. So, let's say the executive authorizes the action. The tools selector has grabbed the email API tool, the permissions checkout, and the executive fires the email payload. But technology is inherently messy and chaotic.
Always.
What happens if the executive tries to send the email, but the external email server is down for maintenance? Or what if the API key the system is using expired 10 minutes ago?
That's where the straight line fails again.
Right. A straight-line system would just blindly assume the text it generated became reality and move on to updating the CRM.
Right, exactly.
The agent needs a way to actually verify the outcome. It needs sensory input.
And this transition brings us to arguably the most critical component in bending the straight line into a functioning loop. The module TrustScreen calls the observer.
The observer.
If we go back to our philosopher changing the tire, the philosopher verbally instructs you to tighten the lug nut, and then, without looking, internally registers that the lug nut is completely tight.
Right, because they said it, so it must be true.
Exactly. The observer is the architectural component that physically grabs a torque wrench and checks the tension on the lug nut. After the executive runs a tool, the observer's sole responsibility is to ingest and parse the empirical result of that specific action.
So it's constantly interrogating reality. It's asking, did the database search actually return a PDF of the invoice, or did it return a null value?
Yes.
Did the email API accept our JSON payload and return a 200 OK success code, or did it throw a 404 error? Basically, the server's way of saying, hey, this endpoint doesn't exist.
Exactly. Did the CRM update execute within the timeout window, or did the connection drop? The foundational rule of agent architecture is that the system cannot, under any circumstances, pretend a task was successful.
It has to have proof.
It must rely on empirical data. If the email API returns an error payload, say, a 401 unauthorized because of an expired key, the observer parses that error code and immediately feeds it back into the loop.
So it tells the brain it failed.
Yes. This specific feedback is what triggers the agent's internal retry logic. It forces the brain to stop, ingest the reality of the failure, and formulate a new plan. It has to decide. Do we wait 5 seconds and retry the exact same tool? Do we switch our approach and attempt to use a secondary backup email server?
Or do we just give up?
Right. Is this a fatal error where we must halt execution safely and escalate the issue to a human operator? The observer is the tether that keeps the system grounded in reality.
Without the observer continuously feeding actual results back into the model, the system will just begin to hallucinate internally, right?
It will stack assumptions on top of failed actions until the entire state of the agent is completely divorced from the truth.
Here's where it gets really interesting to me from an engineering perspective. We have the observer reading the results, tethering the system back to physical reality. But for the agent to actually do anything useful with that observation,
Right, to act on it.
for it to know that it needs to trigger retry logic on the email, or to even remember that it already successfully located the invoice 3 steps ago, it needs a mechanism to store state. It needs memory.
Memory is the connective tissue of the loop. It is the structural element that allows the agent to persist context between each independent cycle of the operation.
I was trying to conceptualize what an agent operating without memory would look like, and the image that popped into my head was a goldfish attempting to bake a cake.
A goldfish. Okay, lay it on me.
You know the urban legend about goldfish having a 3-second memory span? Imagine that goldfish in a kitchen. The planner says, Step 1, retrieve eggs from the refrigerator. The goldfish swims over, pulls open the fridge door, and immediately forgets why it's looking inside.
So confused, it closes the door.
Right. Then the planner reevaluates and says, Step 1, retrieve eggs from the refrigerator. The goldfish opens the door again.
And forgets again.
Exactly. Without memory, every single iteration of the loop is a hard factory reset. It makes accomplishing any multi-step task computationally impossible because the agent constantly wakes up with total amnesia, possessing zero context about what actions it just attempted or what the overarching goal is.
That analogy perfectly illustrates the concept of statelessness. If you want to look at how senior engineers actually solve this goldfish problem, we have to look at how memory is mechanically implemented. It's not magic, it's data management.
How does it actually work in code?
In a robust architecture, memory is stratified into several distinct layers. First, there's short-term memory, which is often managed simply by expanding the LLM's context window. This holds the immediate running log of what just happened.
The recent history.
Right. Every time the loop spins, the observer's findings are appended to a running text log, which is then fed back into the LLM prompt on the next cycle. It literally says to the brain, here is the original goal, here's the plan, and here is a log of the 3 things we just did.
But wait, if the loop has to spin 15 or 20 times to solve a complex edge case, doesn't that running text log get massive?
Oh, it's huge.
Doesn't that start hitting the limits of the LLM's context window? Not to mention driving up the API token costs astronomically.
That is exactly the kind of engineering challenge you face in production. If the prompt gets too long, you encounter latency issues. The system takes 20 seconds just to read its own memory before taking a single step.
Nobody wants an assistant that takes 20 seconds to think.
Exactly. You also run into the lost in the middle phenomenon, where LLMs tend to forget instructions buried in the center of a massive prompt.
Oh, I've seen that happen.
To solve this, senior engineers implement long-term memory, which utilizes entirely different technology, typically vector databases.
Vector databases. That sounds intense.
It's actually quite elegant. Instead of cramming the entire history into the active prompt, the agent summarizes its past actions and stores them as mathematical vectors in a database. When the agent needs to recall a specific detail, like a user preference it learned 3 days ago, it executes a semantic search against that database.
So it only pulls what it needs.
Exactly. It retrieves only the highly relevant context and injects just that specific memory into the current prompt. Memory isn't just a bucket, it's an active, managed system. It holds the planner's roadmap, the execution logs, the raw data retrieved like the actual text of our invoice, and the user's overarching constraints.
Without it, the loop just spins its wheels in the mud eternally.
Just opening and closing the fridge door.
Okay, let's take a breath and zoom out to look at the machine we've just built. We started with a brittle straight line, and we have successfully bent it into a governed mechanical loop.
It's a complex machine.
We have a user goal that flows into a planner. The planner decomposes the goal into a sequence. The LLM brain reasons through the steps one by one. The tool selector and the executive act as the hands, interacting with the real world, heavily gated by permissions.
Yep, you've got it.
The observer acts as the eyes, verifying the empirical results of those tools, and the memory persists the state of the world so the loop can iterate intelligently. From a high level, it sounds incredibly robust.
It does.
But Trustgren makes a point of emphasizing that for this architecture to actually survive deployment in the real world, especially in high-stakes environments like a corporate financial institution, a healthcare network, or enterprise logistics, it needs even more armor.
It absolutely does.
It requires ironclad safety mechanisms and dedicated observability so human engineers can actually monitor its behavior.
And this brings us to the final critical protective layers of a production-grade architecture. Guardrails and logs. Let's tackle guardrails first.
Okay, lay it on me.
Earlier, we discussed permissions, which are essentially binary switches that dictate whether the agent has authorization to use a specific tool.
The bouncer.
Right. Guardrails are significantly more advanced. They are the dynamic safety rules built entirely around the perimeter of the loop. They define the non-negotiable operational boundaries of the system.
If permissions are the bouncer at the door, checking IDs, I'm struggling to see exactly where a guardrail fits in mechanically. Is it like the club manager standing behind the bouncer, watching how people behave once they are inside?
That's a great way to think about it. A permission check simply says, yes, this agent session has the cryptographic key required to invoke the email tool. A guardrail, on the other hand, monitors the context, the payload, and the conditions under which that tool is being used.
So it looks at the content itself.
Yes. Guardrails utilize techniques like semantic routing to dynamically intercept and analyze the data before it hits the executive. For instance, a guardrail might inspect the outgoing summary of our invoice.
What is it looking for?
Well, if it detects a string of numbers that matches the format of a social security number or highly confidential pricing tiers, the guardrail will forcefully scrub that personally identifiable information from the payload before the agent is permitted to transmit it to an external server.
Wow. So it redacts on the fly.
Exactly. Guardrails can also detect if a user prompt is actually a malicious prompt injection attack, trying to trick the agent into ignoring its instructions. And crucially, guardrails are the architectural layer where we enforce mandatory human approval checkpoints.
Human approval in the loop. So the agent is churning through its plan. It gets to a critical juncture, say, right before it actually executes a wire transfer, or right before it permanently overwrites a massive CRM file. And the guardrail literally pauses the execution loop.
Yes, it creates a hard, stateful stop. It pings a human manager on Slack or email and says, I've prepared this action based on this reasoning. Do I have permission to proceed?
That is brilliant.
The agent suspends its current operational state inside its memory and it waits. It will not allow the executive to proceed until it receives a specific cryptographic sign-off, essentially a secure digital signature from an authorized human operator.
So it can't just bypass the human?
No, it's mechanically impossible. This is the cornerstone of building a trusted automated system. You don't trust the model, you trust the guardrail surrounding the model.
Because the model is just a brain guessing words.
Exactly. But this raises an important question regarding observability. What happens when something inside this complex loop inevitably fails, breaks, or produces a result that makes absolutely no logical sense?
That's where the logs and tracing infrastructure comes in, because without them, you are essentially trying to debug a black box.
It's impossible.
If an agent fails silently in a production environment and you don't have logs, how do you even begin to fix it? You can't just type into the chat window, hey, why did you delete that database? Because the LLM doesn't actually know. Its context window has moved on or the session was terminated. It has no persistent awareness of the error outside of what was recorded.
If you attempt to operate an agentic system in production without comprehensive logs and tracing, you are flying blind. Logs are your only diagnostic lifeline. A production architecture records absolutely everything.
What exactly gets logged?
The logs detail exactly which specific tool was invoked by the tool selector, down to the millisecond. They capture the exact raw JSON payload that was transmitted to the API, and the exact raw payload that the API returned to the observer.
Every single interaction.
Yes. And perhaps most importantly, tracing mechanisms record the internal reasoning graph. They document why the planner structured the sequence the way it did, and why the brain selected a specific approach based on the context it had at that precise moment.
So if a user complains that the agent sent a highly aggressive email to a client, an engineer can pull the trace, walk backwards through the loop, and see exactly what went wrong.
Yes, they can see. The observer received a malformed error code from the database, which confused the brain's context window, which caused the planner to drift and mistakenly select the escalate issue tool instead of the retry tool.
So you can actually pinpoint the failure.
Exactly. Without that trace, you are just guessing at ghosts in the machine. This brings us back to the ultimate contrast between the demo mindset and the senior engineer mindset.
The straight line versus the loop.
Right. A junior developer builds a straight-line script designed to work perfectly exactly one time under highly controlled ideal conditions simply to impress an audience.
The magic trick.
A senior software engineer builds a complex loop with the baseline assumption that every single component will eventually fail.
Because it will.
They design the architecture so that when a tool breaks, an API drops, or a model hallucinates, the system can be gracefully suspended, seamlessly debugged via logs, structurally monitored, safely retried, and ultimately trusted by the end user.
It's engineered resilience.
Yes. Real enterprise systems are defined by those harsh operating realities. Reliability metrics, observability, managing latency and token costs, enforcing security boundaries, and integrating human approval. Trust does not emerge from a language model's ability to generate impressive, human-sounding text. Trust is the byproduct of governed, verifiable execution.
Trust is the byproduct of governed execution.
Yeah.
I want everyone listening to just mentally underline that phrase. Okay, we have systematically explored every single component of this architecture, and now I want to do something really ambitious to tie it all together.
Let's do it.
The Trust Grin breakdown concludes with what they describe as a senior engineer's whiteboard masterclass. They bring every module we've discussed into a single flow. So let's do it. Let's dynamically walk through this entire architecture, exactly as a senior systems architect would draw it out with a dry erase marker, connecting all the boxes.
Okay, I'm ready. I'll draw it out with you.
I'll start at the top of the board. Okay, top center of the whiteboard. We draw a large circle. This is the user goal, our prompt. Find the invoice, summarize it, send it, and update the CRM. From that goal, we draw a thick arrow pointing down. Where does it hit first?
That arrow flows directly into a box labeled the planner. Because, as we established, the very first computational job is deciding the navigational path, not just blindly guessing at an answer.
Right.
The planner ingests the goal and decomposes it into a rigid sequence of actionable steps.
Okay, so the planner establishes its sequence. Step 1, find invoice. It draws an arrow over to the LLM.
The planner hands the current environmental context and the specific instruction for step 1 to the LLM reasoning engine, the brain. The brain analyzes the context and reasons about the logical move required to fulfill that specific instruction.
The brain figures out it needs to search, so it draws an arrow down to the tool selector.
The tool selector intersects the brain's intent and maps it to a concrete capability. It evaluates its JSON schema and identifies the secure internal database tool.
Then what?
The tool selector then passes the baton down to the executive. The executive checks the cryptographic permissions, confirms authorization, and actually fires the network request to the database API.
The tool fires into the external world. Now we draw an arrow curving back up from the tools, pointing to the observer.
The external database responds. The observer catches that response payload. It physically verifies the empirical result of the API call. It checks. Did we actually receive a PDF file of the invoice, or did the search time out?
Let's assume it's a success. The observer draws an arrow over to the memory and the logs.
The memory layer ingests the actual text of the invoice and updates the system's state to reflect that step 1 is complete. Simultaneously, the logging infrastructure records the exact API response time, the latency, and the data payload for the engineering team to monitor.
And from that memory box, the arrow loops all the way back around, pointing straight back to the planner and the brain.
Passing the new context so they can initiate the exact same rigorous process for step 2, the summary.
That is the architecture in motion. It loops. Find the data, verify loop, generate the summary, verify loop, send the email, verify loop, update the CRM, verify loop. The execution is grounded in reality and fully traceable at every single turn of the wheel.
It's beautiful when you lay it all out like that.
It really is. And here is the most crucial paradigm-shifting takeaway from this entire whiteboard exercise. We have drawn this massive, multi-step iterative loop. Where on this whiteboard is the final response to the user? At what point does the agent actually output a message to the chat window saying, "I'm done"?
Only after that entire loop has successfully completed for every single step of the planner's roadmap.
So it doesn't talk while it works.
No. Only when the CRM API returns a success code and the observer has empirically verified it, and the memory has recorded the final state, should the system finally exit the loop and produce a final conversational answer to the user.
Because that final answer is fundamentally different from a chatbot's response. It is no longer just a confident statistical guess generated inside a vacuum by a text predictor.
No, it's grounded.
That answer is genuinely mechanically trustworthy because it is backed by physical planning, actual verified tool use, strict empirical observation, persistent state memory, and highly traceable logs. It reflects actual verifiable work completed in the outside world.
That is the design pattern you must remember. You allow the model to reason, but you force the surrounding system architecture to verify. This whiteboard flow is the ultimate checklist you need to take with you into the real world.
It's a literal cheat sheet for evaluating tech.
Yes. The next time a software vendor, a startup founder, or a colleague pitches you an AI agent, do not let them distract you by talking about how many billions of parameters their underlying model has.
Parameter count doesn't matter here.
Ask them architectural questions. Ask them, where is your dedicated planner module? What specific API tools does the executive have access to? How are you managing context window limits and memory between steps? How does your observer verify a failed tool call? Where are your semantic guardrails? And where can I view the raw execution logs?
And if they can't answer?
If they stare at you blankly or if they can't answer those structural questions, they haven't actually built an agent. They've just built a very expensive straight-line demo.
So what does this all mean for you listening right now? It means your fundamental perspective on this technology should now be permanently shifted. You are no longer looking at AI as some magical, omniscient chat box that just natively knows how to do your job.
You are looking at it for what it actually is.
A highly governed, mechanical loop of execution. It is an engineering system of checks and balances. And as Truscrin teases at the very end of their architectural breakdown, this loop is just the foundation.
It's just the beginning.
They point toward future deep dives comparing these agent architectures to standard ORAG systems, retrieval-augmented generation, and exploring how multiple specialized agents might interact with each other. It shows that we are just scratching the surface, there's immense nuance to uncover, and there's always more to learn in this space as the engineering evolves.
And internalizing these deep architectural differences is exactly what will separate the organizations that successfully deploy automated systems to generate real, measurable value from the organizations that get endlessly bogged down in frustrating cycles of failed prototypes and security breaches.
Absolutely. The architecture is the moat. But before we completely wrap up this deep dive, I want to leave you, the listener, with a final lingering thought.
Ooh, I love a good lingering thought.
I want to give you something provocative to chew on that builds on the mechanics we've explored today. We talked extensively about guardrails. The source material highlighted the absolute, strict necessity of human approval checkpoints as a vital safety mechanism before high-risk execution.
Right, the manager signing off.
Yet, paradoxically, the entire driving purpose of building this intricate, looping agent architecture, the planner, the observer, the automated retry logic, is to achieve autonomous execution toward a complex goal without us having to hold its hand. So here is the tension I want you to ponder over your next coffee.
Let's hear it.
As these architectural loops inevitably become faster, as the underlying reasoning planners become demonstrably smarter, and as the error handling and retry logic become astonishingly reliable, as these agents become deeply, invisibly embedded into our minute-by-minute daily workflows, how quickly will our human definition of approval begin to shift?
Well, that's a good question.
How quickly will we transition from carefully, meticulously verifying every step like an engineer checking system logs to simply blindly trusting the loop because it's usually right?
Because it's easier to just click approve.
Exactly. And if this invisible background architecture is doing all the heavy decomposition, all the sequential planning, and all the multi-step problem solving for us day in and day out, what happens to our own biological human muscle memory for complex critical thinking?
That is the real diagnostic muddy water we are stepping into. We are engineering systems to offload our cognitive friction, but friction is often what keeps us sharp.
We spent all this time figuring out how to bend the straight line into a loop, but we might just find ourselves caught inside of it. Thanks for taking this deep dive with us. We'll see you next time.